Our work is focused primarily on providing robotic orthoses to assist individuals such as this. This young woman had a traumatic brain injury as a result of a car accident and has been left with severely impaired hand function on her right side. This impairment interferes with her ability to perform basic activities of daily living. Assisting her in opening and closing her hand would restore some of this lost function. To achieve this, we've previously designed and constructed a hand orthosis for providing extension assistance. This device uses Bowden cables to transmit forces from an actuation unit placed on the upper arm to an orthosis on the hand. This preliminary design incorporates position feedback on the linear actuators for basic position control.
Previously developed intent detection techniques such as the toggling foot pedals, speech commands, and EMG sensing resulted in limited performance. Taking inspiration from ongoing research on learning-based methodologies for pick-and-place robots, we decided to develop a novel technique that will fuse multimodal sensor data to measure human intent for grasping.
The overall controller is categorized based on the tasks to be performed. The first is a compliant controller to emphasize safety of the wearer while avoiding discomfort. A number of sensors were integrated into this design to provide feedback for the control loop, highly accurate flexible bend sensors to help determine the position of the fingers, and current sense amplifiers at the motors to implement force control. The simulation shows the position sensing and torque control in action. The second task performed by the controller is a vision-based intent detection. First, IMUs mounted on the hand orthosis and camera are used to generate position transforms for the field of view. An RGBD camera is used for visual sensing, as the depth map can be used to map surfaces of the objects and generate the corresponding grasp regions. The point cloud is segmented for background removal and clustered to formulate the object surfaces. Centroid detection gives us object grasp regions. The final aspect of the intent detection controller is tracking objects and the hand orthosis in the field of view. A real-time 2D object detection algorithm was used with the regions of interest then projected into 3D space. The hand tracking was achieved through the use of AR markers placed on the hand surface. The integration of all the sensors can be seen in this demonstration. The depth camera was head-mounted on the subject to emulate view of the manipulation space. The floating window shows the feed from this camera, tracking the hand, detecting objects, generating grasp regions, and calculating distances. Once the conditions for grasp are satisfied, the controller is activated, sensing finger positions and implementing force control. The entire system seamlessly replicates natural intent and allows the subject to grasp and drop objects without using invasive brain-computer interfaces. The next step for this project is to study the efficacy with afflicted patients.